Hey, what's up, everybody? I realize I'm backlit, but this is the first time in a long time that I've had time to be able to communicate to you folks, so I'm excited to finally knock this video out. Today, we are going to be talking about the conformal transformations of the plane in terms of the stereographic projection of the sphere. Specifically, we're going to do kind of the standard thing where we take R2, embed it into R1, 3, the thing we've been advertising, look at the light cone, because it itself is invariant under the Lorentz transformations, the group SO1, 3, and see how the six-dimensional Lie algebra of those transformations maps directly to the six-dimensional Lie algebra of conformal transformations of the plane. In other words, we're going to be doing explicit calculations. So let's get started. One thing we need to recover is the stereographic projection formula from the sphere, the two-sphere in R3 down to the plane. Specifically, we need to investigate this for the case of the non-unit sphere, a sphere with arbitrary radius. Why? Well, let's go back to the light cone. So in R1, 3, right, we consider the coordinates t, x, y, and z. And the light cone, that is to say the null cone, that is to say the set of vectors in that space under that pseudo-Euclidean metric that have zero magnitude are given by the equation minus t squared plus x squared plus y squared plus z squared. We call it a variety, not a manifold, because the origin is singular. There's a point there. And so for all intents and purposes, what we're really interested in is kind of 1/2 at a time, at least in this context. So we'll be specifically looking at if the time axis goes up and down the light cone, we'll be looking at the top half. Let's consider a slice of fixed time, right? So like t equals to capital T, right? So the corresponding slice through R1, 3, which is hard to draw here, but you can imagine it being R3. It's a three-dimensional space dictated by the light cone equation, right? So now we're going to fix t to some constant plus t. So it's x squared plus y squared plus z squared is equal to t squared, right? In other words, it's a sphere with non-unit radius. It's not the unit sphere. So let's go ahead and go through the entire stereographic projection process again to get the relevant formulae. So we want to look for the North Pole. The North Pole is at the point 0, 0, capital T, right? And we're looking for an arbitrary point P on the sphere somewhere. And so we want to form the line between them. That line is given by, gamma, which is parametrized by some value S. And so we can write this down in vector notation as, x, y, z minus t, whole thing times the parameter S, plus just the North Pole, that is to say 0, 0, and t. This way, when s, our parameter on the line, is equal to 0, we're at the North Pole, and then when s is equal to 1, we're at that point P, and then we can just continue with values of s in the reals all the way up and down to get to wherever we want to on the line. In particular, we're interested in that point where that line intersects the plane z equals 0. So when we set that up, we can define our coordinates from the stereographic projection, right? Like say big X and big Y, and z equals to 0 implies that the value of that parameter is given by t divided by t minus z. Good, so now we know how to create this map from R3 down to the plane, the stereographic projection map. And that's just given by, the planar coordinates, let's say big X and big Y is equal to little xt over t minus z and little yt over t minus z, respectively. Super easy. And we can also invert these just like we did last time, and I leave it to you as an exercise to kind of invert this, but it's really straightforward. You follow the same logic, and you can see that it's the kind of the similar things, factors of t squared, where once there was nothing, or at least an implicit one. Good. Okay, so now let's investigate what it looks like when we actually perform Lorentz transformations in R1, 3, kind of on the light cone, and how those map down to the plane. So specifically, what we're going to be considering is a subset of all possibilities, just for the sake of pedagogy, for the sake of making a video that's sensible, that you can understand and remember, and also it's not too hard. So we're actually going to be focusing on a very narrow set of points. We're going to be looking at transforming the unit circle on the plane R2, and of course that maps to a unit circle in R1, 3 as well. So specifically in the case of R1, 3, we're going to be looking at the case where time is equal to t is equal to 1, x and y are whatever they are, that is to say, whatever they will be, once we also impose the constraint that z is equal to 0. So we're just going to be looking at that plane at that constant t equals 1. Good. Okay, so this gives us a coordinates, t, x, y, z is 1, a, b, say, and 0, or 1, x, y, and 0, however you want to think about it. So that's our parameterization. Okay, good. So now let's go through the individual Lorentz transformations of R1, 3. So recall that the Lorentz transformations in this instance break into two categories, the rotations and the boosts. The rotations are things that rotate coordinates like you're familiar with, right? Like x with y, or y with z, or x with z, right? And so for the specific case of x with y, we are looking at something that involves cosines and sines. So x, y goes to x times cosine theta, plus y times sine theta, and then y goes to y times cosine theta minus x times sine theta. Easy kind of stuff. For the case of boosts, which involve this kind of pseudo-Euclidean direction, this kind of awkward minus sign thing, this time direction, instead of using sines and cosines, we use sinches and coches, the hyperbolic versions of these things. And so I'll just parameterize that by an angle as well, say phi, and so say like t with x, t with y, and t with z gives us the other three boosts. So t with x would go to cosh, t goes to t times cosh phi plus x times sinh phi, and x would go to x times cosh phi plus, an important plus, t with sinh phi. Let us begin by exploring the different transformations. So for the specific case of the xy rotation, we know it's trivial, so we don't even worry about it, right? xy rotates, it's the same. It's the same thing as it is in R1, 3 as it is in the plane. Good. Now, let's consider the boost t and z direction. So from the plane's perspective, these are the two hidden directions that we're going to rotate between, and let's see what happens. So we take the coordinates in our restricted set now, which is 1, a, b, and 0, and we apply the Lorentz boosts. Now, z is equal to 0, so nothing happens from that regard. So basically what's going to happen is time is going to map to t cosh phi, and z, which was 0, now maps to just simply t sinh phi, but t is equal to 1, so we can actually throw that t away. That's just the way we've set things up. And so really what happens is a and b go to themselves. So when we look at the projection down to stereographic plane, what we end up having is x, big X in the plane, goes to itself times t prime divided by, which is, this junk, divided by t prime minus z, e to the phi times cosh phi. And the point is, x gets scaled and y gets scaled by the same factor. Think it, e to the phi times cosh phi. Now, I got to make sure that that plus sign is right. You see the point. The point is that x and y map to x and y times a parameterized constant. So what we've found here is that the boost in the hidden directions, right, this t with z, gives us from the from the plane perspective, the conformal transformation associated to dilatations or scaling. Cool. Okay, so that's two transformations down. Let's see if we can get the rest of the other ones in. So next, let's consider the boosts. These are pretty symmetric, right? So t with x or t with y in R1, 3. So from this perspective, what we need to consider is coches and cinches again. And so let's start with our original point, 1, a, b, and 0. So this is going to map to t goes to cosh phi plus a sinh phi, where a was, originally our little x direction. And then x will go to a cosh phi plus sinh phi. One more time. B goes to b, so no big deal. So what happens here, what we observe is that in the plane, during the stereographic projection now from R3 down to the plane, what we're going to see is that we have x prime times t prime over t prime minus z prime, right? So in other words, what we're just going to see is a cosh phi plus sinh phi, because the t primes stuff cancel and z is equal to 0, so it's no big deal. So what we see is that a, in other words, gets mapped, or x coordinate on the plane gets mapped to a slightly different value, and the b coordinate doesn't get mapped at all. And similarly, if you were to look for boosts in R1,3 that mix y with t, you would get that in the plane projected down, x wouldn't get moved at all, but y would get shifted by the same amount, right? By the same kind of cosh phi b plus sinh phi. Now, to understand what this means in terms of the Lie algebra, we need to go to infinitesimal values of phi, that angle, and we see that, of course, cosh phi approximately equals 1 for small angles, sinh phi approximately equals phi for small angles, and so really what we have here are the translations in the plane. So in other words, boosts that mix the coordinates x and y with time correspond to, well, stereographically projected down to the plane, translations, the two translation conformal transformations. So we have the two translations, we have the rotations, and we have the dilatations. 2 left to go. All right, and the battery and the camera is running down, so let's see if we can do it. Now, finally, we have to look at the rotations between x, y, and z, this kind of third coordinate. So let's go and do that one at a time. So now we can throw away our knowledge of coshes and sinh, and we're going back to cosines and sines. So in other words, our original point, 1ab0, is going to go and get mapped to 1a cosine theta plus 0, because z is 0, b, and then minus a sine phi, because now z gets rotated and picks up some of that x component. So now let's project that through down to the stereographic projection map, and we find that our coordinate x in the plane gets mapped to a cosine phi, or x cosine phi, divided by 1 plus x sine phi, theta, sorry, and y, the numerator gets mapped to itself, but the denominator also picks up that component from the z, right, which is going to be, so y goes to y over 1 plus a sine theta as well. And so this is kind of a weird one, right? This is kind of a quirky combination, but in other words, the pair a and b, the pair x and y, if you like, gets mapped to something that's like x over 1 plus x sine theta times cosine theta, and y over 1 plus a cosine theta. Yes, we have these fractional linear transformations of the coordinates in the stereographic projected plane dependent upon the parameter theta. They are the special conformal transformations, as we will now show. But before I do that, I want to point out that I can do the exact same thing with the y-coordinate by simply rotating in R1,3 little y with little z. You get just replace a with b and replace x with y, and you will have exactly the same formulae. Good. So now, to prove that this is in fact a special conformal transformation, we need to recall that the special conformal transformations in the Lie algebra are the quadratic terms. That is to say, they depend on not just constant times x. They're not linear. That's constant times x squared, if you like. So in order to do that, we have to consider infinitesimal transformations of the variable theta. So the best way to do that is to simply Taylor expand, and so the kind of naive way that we can go about doing that is look at x prime, take a derivative of x prime with respect to theta, set that derivative equal to 0, that is to say we're Taylor expanding around theta is equal to 0, and then we'll have a little delta theta out in front, and that will be our new parameter that will essentially be the kind of the one form in the Lie algebra. Good. So pursuing this path, we find all of the cosine thetas are effectively 1s, and all of the sine thetas are effectively 0s, and so, lo and behold, we have infinitesimally that x not only goes like, x times some constant parameter, but x goes to itself times a constant parameter. In other words, x goes to x squared times a constant parameter, which, as you integrate, that value becomes a special conformal transformation. And exactly the same thing again happens with y. Great, so that's all for the special conformal transformations of the plane. All 6 of them are now accounted for explicitly. I'm glad to get this video done, to get it out, get it shipped, get it to you. Hopefully that answers some questions you may have had or clears up some understandings. If not, if you're going to be going to study conformal field theory, as we will soon, hopefully it sets the stage well enough. With that, let's stop talking and start working on another video. See you as soon as we can.